All right, so let's continue from our last time's discussion on a periodic limit cycle in continuous time. Okay, so we have shown that a limit cycle in continuous time always have a zero Lyapunov exponent. So what that means is that there is one mode of perturbation, right, where if you perturb only the initial condition, not the system parameter, and you follow how that perturbed solution is going to evolve in time and compare that solution to the unperturbed solution, there is always going to be a difference between the perturbed and the unperturbed solution that's never going to grow, neither is going to decay. Right? So that's what the zero Lyapunov exponent means. And we have shown that that mode of perturbation that doesn't grow nor decay is actually in the direction of the time evolution. So that is du dt, or f of u, right? So that's the mode that doesn't decay, corresponding to the zero Lyapunov exponent. There is what? Sorry?
I have a question.
Yeah.
There are some Lyapunov exponents close to zero. So those are related. We can say these or those Lyapunov exponents that are close to zero are also zero, but the decay or growth is linearly. It's a linear.
Yeah, so if you have a mode of perturbation that grows or decays in a linear, I mean, you can decay in it. Well, yeah, if you grow linearly or decay like 1 over t, right? Not exponentially, a sub-exponential growth or decay. According to the definition of the Lyapunov exponent, right, you take the logarithm of that magnitude of the perturbation and divide it by the time. Any sub-exponential increase or decrease would lead to a zero Lyapunov exponent. Okay. Yes. So yeah, if you have any mode that doesn't grow exponentially, that grows but doesn't grow as fast as exponentially, or decay but doesn't decay as fast as exponentially, you are gonna get a zero Lyapunov exponent. Okay. It's just in this case, if we have a limit cycle, we can prove that the mode actually doesn't decay nor grows, because we can show that that mode is actually equal to Vt equal to f of ut, right? And f of ut, if f is a continuous function in a compact domain, then there is always going to be an upper bound for f, right? So f is not going to go to infinity. Also, if the system doesn't go into a fixed point, then we can also show that f doesn't go to zero, right? So basically, you will have a finite Vt that's neither going to grow nor going to decay. Okay, we started showing the consequence of that Lyapunov exponent, the zero Lyapunov exponent, right? So that is actually a preview of what's going to come in chaotic system, which have not only zero but also positive Lyapunov exponents. So even if you just have a zero Lyapunov exponent, what happens is that although the homogeneous tangent equation, which models the evolution of an initial condition perturbation, is not going to grow, but the inhomogeneous tangent equation, which governs the evolution of a solution, which governs the evolution of the difference between two solutions, one with a perturbed parameter, not just the initial condition, a perturbed parameter, one with a unperturbed parameter, a slightly different parameter, right? The difference between these two solutions would now actually grow linearly. And the linear growth is actually because of the perturbation in the parameter may slightly change the period or frequency of the systems, right? So if your parameter perturbation actually changes the period or the frequency, what happens is that the linearized solution would actually grow indefinitely, linearly in time. So that's what's demonstrated over here. So the solution to the tangent equation, the inhomogeneous tangent equation, when we perturb, what did we perturb? Let's see. we actually perturb the first parameter, which is mu, right? So basically we added a 10 to the minus 100j. So for example, if we if we don't perturb the initial condition, we just add the let's say u0 plus 0j. So the only purpose of this line is to make u0 a complex variable as opposed to a real variable, just change the type, right? I can also say u0 equal to array u0, the type equal to complex. Okay, then what we should see, let me just make sure I did import all the stuff I need to import. Actually, let me just do it over here. From scipy.integrate import solve IP. Then I should be able to run these, I think. So if I don't perturb the initial condition at all and only perturb the parameter, I should also see this. Haven't finished yet. I should still see the linear growth of the perturbation, right? Except for now the start of the perturbation should be exactly 0 because the initial condition is not perturbed. Right, so basically we start with 0 and we still see a linear growth on the long term. All right, questions?
So here we don't expect that the error grows exponentially, right?
No. Yeah, we expect that the difference between the two solutions would have a linear growth. Okay, so now this lecture, let's focus on figuring out actually how to do sensitivity analysis of statistics. So what do I mean by statistics? Statistics J bar, right, is actually equal to, there are two definitions and they are equal if the system is ergodic. So one definition is the limit of the number of ensembles goes to infinity, right? And the number of ensembles goes to infinity. It's basically the expectation. Let me just write it as expectation. So one definition is the expectation under the equilibrium distribution. Let me say rho, right? Of J of U. So basically, if I have a bunch of solutions distributed on the attractor, right? So in this case, the attractor is a limit cycle attractor. If a U is distributed according to the equilibrium distribution, right? And in our case, if we have a attractor like a limit cycle, the equilibrium distribution would be a distribution on this limit cycle. It would be denser if the trajectory slows down over that point. If the trajectory accelerates around that point, the equilibrium distribution would be sparser, right? It would be less dense over there. So basically, remember, like if a system is ergodic, the equilibrium distribution is just the percentage of time an infinitely long trajectory spans over that portion of the phase space. So if the system is ergodic, it is also equal to a limit of t goes to infinity, 1 over t times integration from 0 to t, j of a solution ut dt, right? So that's basically a time average over a time length of big T, and take the limit of t goes to infinity. Okay, what we are introducing here is that now my u is not just a function of time, but also a function of parameter. So now if I have a du dt equal to f of u and s, right? Then the two definitions needs to be modified a little bit. In the first definition, what is going to be changed by the parameter? What is the effect of the parameter change in the first definition, the expectation? Right? Is J changed at all? No, right? I'm assuming I'm using the same objective function that doesn't depend on the parameter, right? I mean, if the objective function does depend on the parameter, which is often the case if you look at like aircraft design or something like that, then there is a separate component, right, of the sensitivity. We'll look at that later. That's the easy part. The hard part is how the solution is changed by the parameter, which it then changes the objective function. So in the first definition, what is changed really by the parameter value? Yeah, is the what? The distribution, exactly. In the first case, I should be really writing that as a rho as a function of S, Ju, right? Okay, so because now I'm looking at the distribution, an infinitely large ensemble on a different distribution. For example, again going back to our van der Pol oscillator, if we change our mu, right, we should see that actually two things are happening at the same time. One is that the shape of this limit cycle is going to change, right? So remember, like when mu is equal to almost 0, right, the second part is almost gone, and you just have a harmonic oscillator, which on the phase space is a perfect circle, right? So that means the smaller mu is, the more similar that limit cycle should be to a perfect circle. That means the shape is going to change. But there is another thing that's going to change, is that the density on this trajectory is going to change. So what does that mean? That means if you remember, the y-axis is just the dx dt, right? That means when the y-axis is large, right, like over here, the trajectory should really go over very fast, like over here. But when the y dot is, when y, which is x dot, is small over here, the trajectory should slow down and spend more time over here, right? So that means the density distribution on this limit cycle is not going to be uniform. While we change the parameter, the density is going to change. And in particular, when mu is close to 0, when you get a limit cycle, right? The harmonic, when you get a harmonic oscillator, the harmonic oscillator actually spends equal time on every part of this circle. I mean, just goes on the circle at a uniform speed. So the density is the second part that's going to change. These are actually the same as what we are going to be discussing in the chaotic case. That is, as you change the parameter of a dynamical system, or you change the dynamical system, right, in a continuous or smooth way, the equilibrium distribution, or the ergodic measure, right, ergodic probability measure in the phase space is going to change, and that's reflected in two ways. One is the attract itself is going to move, right, or the support of this basically support of this measure is where the measure is non-zero, right, is going to change, and also the distribution on that support is also going to change. Okay, but in the second case, what is going to change, right? In the second definition, when we change S, what is the only thing that's going to be different? The T is not going to be different. I mean, it's taken to infinity anyway, right? J is the same. So the only thing that's going to be different is U, right? The trajectory itself is now changed or modified by the parameter. So in the second definition, we just write a limit of t goes to infinity, a time average of j as a function of u, t, and s. All right. Okay. So let's actually start to look at the system, at the sensitivity of j bar, right? So let's say, what if we want to compute the derivative of j bar with respect to the parameter? Okay, so which definition do you think is easier to use when we want to compute the sensitivity? Actually, which definition is easier to use when we just want to compute J-bar? The second one, right? Because the first one actually requires you to compute the density, and especially in a high-dimensional phase space, computing the equilibrium density is not an easy task. So let's just follow the second approach. And the obvious question is that, what if we can just take the derivative all the way into u, right? That would be easy. In some sense, we have already computed over here, right, a tangent solution in inhomogeneous tangent equation that is already the derivative of the solution u with respect to s, right? By perturbing this s, in this case the mu, from 1.0 to 1.0 plus a small perturbation, right? And look at that small perturbation, which is the imaginary part of this solution, right? We are effectively computing already the derivative. Actually a finite difference, but it is effectively the same as derivative because the amount of perturbation is so small, right? 10 to the minus 100. So we are effectively computing the derivative of the solution u by just looking at the imaginary part, right? The solution u with respect to that parameter. Okay, so basically we already know the derivative of u with respect to s, right, as a function of t, right? And that's basically our solution v, satisfying dv dt equal to partial f partial u times v plus partial f partial s, right? So that's basically the solution to the tangent equation. We already know how to solve. Okay, what if we can use the chain rule to take the derivative dds inside the limit and inside the average and use a chain rule, right? So the first question is that equal to the limit of t goes to infinity 1 over t dj ds, which can be chain ruled as dj du times du ds. Right, so this is just simply a application of the chain rule. The only questionable part is if we can take the derivative inside the limit, right? Everything else is just the standard calculus. Remember the integral, right? The both sides of the integral doesn't depend on s, so we can take the dds into the integral, and then dj ds, of course, is dj du times du ds, right? There is nothing wrong with that. The only questionable part is the derivative itself is a limit, right? If you think about the definition of a derivative, it's the limit of epsilon goes to 0 of a ratio, right? And there is another limit. So two limits. Can you exchange two limits? Well, sometimes you can, sometimes you can't. It depends on the conditions, right? I mean, the primary condition is that do you have uniform convergence or not? I'll remind you that later, like about the exchange of the two limits. But if we can exchange the two limits, then this is going to be correct. Okay, so why don't we just try it computationally to see if it works? Okay, so we already have the UDS. Let's just let's just take an example, right? Let's just take an example. Example J of U equal to, let's just say U1 squared or X squared in our case, right? Like in the van der Pol oscillator, U has two components, X and Y, right? Or X squared. The y is the time derivative of x, and usually we are more interested in x, so let's just take x squared. The reason we are taking x squared is really it's the simplest function we can look at that's non-trivial. If we look at x, it's trivial because the average would be 0, right? It's a symmetric system. Okay, so if we do that, then dj du would just be what? It's just going to be 2x, right? Okay, let's see if we don't even have to do that analytically. We can just take x squared and look at the imaginary part. That's just automatically done for us. All right, so what we are going to be doing is let's copy this code. And instead of having a single perturbation, well, let's just do this, right? So so instead of well, let me just start n equal to 1. So we will just look at one solution, okay, with the perturbed parameter, and we get the solution u, and in particular the j would be equal to u0, because I just have n equal to 1, right? I would just have j is equal to u0, 1. The second index is the number of solutions, okay, square. Okay, that's my j as a function of time. Now my j bar is an average, right? So j bar is equal to j dot average. Actually, let me start with a few solutions. 10 solutions. J would be I would get 10 different j's, and when I take the mean, I should be taking the mean over the first dimension, which is the dimension of the time, right? So I get a bunch of j bars, one for each solution. And let's look at what j bar is like. Oh, okay. So j bar has a so basically we see that for all the 10 solutions we get a j bar. We get a real part of j bar that's pretty close to each other, right? A 2.0 something. And the imaginary part is going to be the sensitivity of my j bar with respect to s. Okay, and we see all kinds of values, smallest being 1.9, largest being 5.9. So obviously these haven't really converged yet. So why don't we increase the time by something? Let's say make it 1,000. All right, and this would be 1,000 and be a bit more. Okay, so we increase the length of time by a factor of 10. And now we see that the real part has converged a bit more, right? Previously it's 2.0 something, now it's almost always around the 2.06, right? Okay, but the imaginary part still all over the place pretty much, right? The 1.4, 2.0, maybe it's better a little bit, but not that much better. So let's actually increase it even more. Let's see. Let's increase it to 10,000. Now, actually, it takes some time to do the calculation, do the time integration. All right. Well, actually, so the real part got a lot better, and the imaginary part, starting from different conditions, this seems to be also getting a bit better, except for this. So as you can see that basically we should actually what we should actually plot, right, is the convergence, right? Is that as the time increases, how does the real part converge and how does the imaginary part converge. So let's actually do that. So when we, instead of taking a mean, we should take the cumulative mean, right? We should be taking the J bar should be equal to, where should we start? We should be taking J dot, let's say, cum sum of J in the dimension 1. Okay, so that's a cumulative sum divided by how many time steps we are summing over. So range of 1 to J dot shape 1 plus 1, right? So that's basically goes from 1 to the total number of time steps we have. And let's actually plot both the real and the imaginary parts of J bar. So let's plot J bar dot real, and let's actually make 2 plots. And first the plot plus the real part and the imaginary parts. Actually, let me see if that how that looks like. See, am I doing the calculations right? What do I have? I have 10 by a million, right? Why is it so slow? Oh, I should be plotting the transpose of this. Sorry. Yeah, that's why the calculations are done quickly. Just I think I'm plotting the wrong dimension. I'm trying to generate a million plots. All right. Okay. So we see the real part converges really quickly, but the imaginary part doesn't really seems to be converging, right? I mean, all of them are kind of going to the same value, but at the end they are really still spaced apart, right? So it looks like they are actually converging, maybe converging to different values. So why is that the case? So let's actually, this is really a manifestation of how the inhomogeneous tangent solution having a magnitude that grows linearly. So imagine what we are doing here, right? So we solve the solution. The real part is actually the solution. The imaginary part is the tangent solution, which has an linear growth. Okay. And what we are doing here is we are averaging a quantity that actually grows linearly. Okay, so basically the real part is fine. We are taking a very accurate averaging because it doesn't grow. But when we are averaging the imaginary part, there is a linear growth, right, in the quantity being averaged. And it's the linear growth of the quantity being averaged that makes this finite error even after a million time steps of averaging. Okay, so this is one way to understand why the naive way of sensitivity analysis doesn't work, in the sense that this limit, right, does not equal to the limit of the derivative of the infinite time sensitivity, right? Depending on what the initial condition is, this limit can converge to different values as this one. And as we're going to see for chaotic cases, this limit may not converge at all. Okay. Another way to visualize the inequality of these two limits is by actually visualizing how the finite time average, right? This finite time average looks like as I take t larger and larger. Okay, so let's actually do that. So what we are going to do is we are going to look at the function, the finite time average as a function of the parameter value, and look at how that function would change as the length of the time averaging increases. Okay, so for example here we already have a. Okay, so let me just do this again. We want to really compute a much longer, much finer parameter. So let's make actually 1001 parameters, and let's actually make them start at the same location. Okay, once n, and let's actually make them actually real so that my calculation can be a little bit faster. And the arcs would be equal to, okay, so here's my initial solution, but I'm going to make my mu actually a function. So mu is going to taking 1001 different values from 0 to 1. And let's look at, let's feed this mu into the differential equation so that we are actually integrating n different solutions, each with a different parameter. Okay, and we are still going to reshape it, and we are still going to compute the j bar, but instead of printing it, we are going to plot the j bar as a function of mu. And I think let me start with something much shorter so that I think that'll take too much time. So let's actually integrate it only for 10 time units and see what the solution looks like. Okay, so well, 10 time units might be a bit small. Let's actually integrate 100 time units and see what it looks like. Right, so this is what we see. Okay, so we see that initially the j bar is an increasing function of mu, and at some point it gets flatter and flatter. But one of the interesting features is this kinks over here. Right, so in order to understand what these kinks are, let's actually plot the 1001 solutions and see what is really contributing to the kinks at around the mu value equal to maybe 0.7 and 0.8, right? Okay, so let's actually plot just the solution, the first component of the solution as a function of time. So solution dot t is the time, and let's look at how the solution looks like. I think I need to transpose the x for the solution to be plotted. Stop it, run it again. Okay, so this is the 1001 solutions. And what you are seeing is something interesting, right? So in the beginning, all the solutions seems to be oscillating at the same phase. But as time goes on, the solution kind of decorrelates, right? And this is exactly because what we discussed before, right? The different parameter values follow slightly different frequencies. All right. And basically this causes the solution to be basically a very different, at very different phase locations on this limit cycle, right? When the solution ends. And what is happening at these two parameter values? It might be difficult to see from here, but this is exactly okay. So maybe maybe I can zoom in a little bit here. What is the best way to do this? So let's zoom in into the last segment of the solution. So let's start from 9,000. Okay, so let's just plot the last 10 time units. Yeah, what you can see is that basically there are two essentially there are two locations, right, where the dependence of the phase on the parameter actually becomes very sensitive, and that's what's creating these kinks. All right. So the obvious question is that as I increase the length of the integration, right, would the kinks become improved? I mean, the problem about the kinks is the following. There are really two problems. One problem is that if my parameter value, right, so one question is this kinks real or not, right? If the kinks are real in the sense that they reflect if the infinite time average have the same kinks, then having the kinks here and taking the derivative at the location of the kinks would actually be correct. It turns out to be not true, right? So the infinite time average is a lot smoother than indicated by these kinks. And the second problem is that when no matter whether you take a derivative exactly on the location of the kinks or at the location of the non-kinky locations, you are misrepresenting the derivative. When you take the derivative at the very steep locations, you are overestimating the derivative. While if you take the derivative at the flatter locations, you would be underestimating the derivative, right? And depending on where exactly you are over or underestimating the derivative by different amounts. That's what we are actually seeing here, right? Different solutions would have different convergence values. So, for example, if instead of integrating for 100 time units, if we integrate by 200 time units, and we take two different values, right? We take two different averages. One is we take the entire 200 time units value, and two is that we are only taking actually j is equal to this. We take two j bars, j bar 1 and j bar 2. One is the first one is I'm only averaging over the first half, right? So this would be the first half of the trajectory, which should give us the same result. And j bar 1 and j bar 2. So we are plotting two different solution values. And so let's comment this out. So what we see is that, okay, the other solution, the yellow solution, which is the blue is the same, right? We are plotting the first half of the integration, which was the same as the average before. But the orange one, this kink disappears, but there are more kinks over here, right? So essentially what we are doing here is that by increasing the length of the time integration, we are improving the value of the time average, but we are actually not increasing the derivative. We're not increasing the fidelity of the derivative of the time integration. The reason is that we see smaller oscillations, but the oscillations are actually in higher frequency, right? The reason for that is that if we average over longer time periods, the end of these longer time periods would be even less coherent, right, with each other. So what we saw before was if we plot the end of the first time period, we saw a substantial amount of decorrelation, right? But let's actually make more figures. Actually, if we make more figures and plot the end of the longer time period, we should see that the end of the longer time period, which we plot as which we average into j bar 2, would be actually even less correlated, right? So this is the end of the first time period, this is the end of the second time period. Okay, so that decorrelation actually makes the makes this objective function having a higher frequency oscillation, even though the magnitude of the oscillation becomes smaller. All right. Does that make sense? Any questions? Yeah.
Is the system ergodic?
The system is ergodic, yes. So we are looking at the van der Waals oscillator, for which all the solutions actually converge to the same limit cycle. And once it converges to the same limit cycle, the speed over which the solution goes around the limit cycle is basically determined by the value of the right-hand side on that limit cycle, right? So there is a unique equilibrium distribution.
And we had a parameter that is perturbed, right?
Yes.
So I expect that we have different objective functions.
We should actually have different objective functions for different parameter values. Yeah, that's right.
But why all of them is converged to just one?
So in this particular case, the objective function, the time average, long time average, the objective function. Okay, so first of all, let me make sure that this is not a convergence plot. This is the x-axis is actually the parameter value. The y-axis is the long time average, right? So this is actually how the long time average depend on the parameter value. So when we're doing sensitivity analysis, we're actually taking the slope of this plot, like dj bar ds. That's the objective we want to compute, right? So what I'm showing here is that the slope of the infinite time plot is not going to be well approximated by the slope of the finite time average, especially if you're unlucky and take a parameter value like in these in the regions where the slope is much larger than elsewhere.
So in the kink, the slope is kind of infinite, right?
It's probably not infinite, but like pretty large. Yeah.
Yeah. So it means that it's very sensitive to. It's like there's a point that is very sensitive to that specific parameter, right?
Right. Yeah. So it is a point at which the end point of the trajectory is actually sensitive to the parameter value.
So it's not a bifurcation.
It's not a bifurcation in the dynamical system case, right? It's just a so let me actually give you a in order for us to understand this phenomenon better, right? Let me use a simpler dynamical system and the simpler objective function, almost the artificially constructed dynamical system, and then almost the artificially constructed objective function, right? And the artificially constructed the parameter to illustrate the same problem. Okay, so let me explain what that artificial problem is. Okay, the artificial dynamical system is a continuous time dynamical system, but in one dimension. Okay, it's just a dx over dt equal to 1, but x is within the domain of r divided by z. So what that means? So r modulus z, right, is the it's known as the periodic domain between 0 and 1. So what does r modulus z mean? R modulus z is basically taking all the real numbers and constructing equivalence classes on these real numbers, where one number is equivalent to another number if their difference is within z, an integer. Okay, so what that means is that 1 is equivalent to 0, right, and is equivalent to 2 and minus 1, etc. So when you take the derivative of x is equal to 1, that means x would slowly go from 0 to 1, which is the same as 0, right? And it would go from that 0 to 1 again. So it's a periodic dynamical system. Okay, and we're going to add a s onto the right-hand side, right? So that's our parameter, which means if s is greater than 0, the system is going from 0 to 1 and back again at a faster rate. All right? Okay, and because we want to construct an objective function on this one, j would be actually equal to sine. We need to make an objective function that's continuous, which means that j at 0 has to be equal to j at 1, right? So let's just make it 2 pi of x, right? So that when x is equal to 0, it's exactly the same as x equal to 1. So this is the artificially constructed dynamical system. And of course, what is j bar? What is the infinitely long time average of sine of 2 pi x if x just goes through the interval 0 and 1 at a uniform rate, no matter what that uniform rate is? It's going to be 0, right? We can show this by actually deriving the solution, right? X would be actually 1 plus s times t, right? And j as a function of t would be actually sine of 2 pi 1 plus s times t, right? So j would just look at it as a function of x would be just a sinusoidal function of t. Over every period, j averages to 0, right? And the maximum and the minimum oscillation on the j bar would actually decrease as a function of t. Okay, so j bar is equal to 0. Then, of course, what is dds of j bar? It's equal to 0, right? It's a derivative of the 0 function, because j bar is equal to 0 no matter what s is. However, let's look at what is the final time average of j. and look at what is the derivative of that finite time average. Here we immediately see a potential problem. Is that what is the rate at which j converges to 0 as time goes? What is the rate of, let me just say, j bar t? We use a capital. Let's actually use the capital T to denote the length of the time averaging as 1 over t j dt. Okay. How fast does the j bar t converge to 0 as capital T increases? Any thoughts?
So for one period, it's going to become 0, right?
Yeah, over one period, over any integer periods, right, it's going to come back to 0, exactly.
So it depends on the 1 over t, right?
It depends on the 1 over t. So let's actually, that's correct. Let's actually show that it is the case, like in by just numerically computing it. So let's make a S is equal to length space of 0, 1. Let's make 1000. Okay, so we are going to be basically taking a bunch of S's. And what t would you want? Well, no matter what t do we want, we actually can compute it analytically, right? So let's see if j is equal to this. What is integral? What is integral of sine of 2 pi 1 plus st dt, right? What is the integral of a sinusoidal function? It's minus cosine, right? Okay, so 1 over t is still here, and we'll take the whole thing out. So we have to take 2 pi 1 plus s. That's the parameter. We're going to divide this and multiply this into dt, and after the integration, it'll be basically cosine of 0, which is 1, minus cosine of 2 pi 1 plus s capital T, right? Okay. And of course, the cosine function varies between 1 and minus 1, and as a result of that, this whole function would differ from 0, which is the infinite time average value, by as much as by something proportional to 1 over t, right? So that's your answer, which is correct. All right. But the problem is that what is the frequency of that function? What is the frequency of oscillation of that function if you think about it as a function of s? There is a cosine of 2 pi 1 plus s times big T, right? So the larger T is, of course, this whole thing is smaller, but the frequency of oscillation of that function would also be faster, right? So think about it as a function that, as t increases, a function that just goes to 0 in its magnitude, but oscillates at a faster and faster rate. Now think about the derivative of that function. Would the derivative converge to 0? It's a question that asks, does the magnitude of the oscillation go down faster, or does the frequency of the oscillation go up faster, right? If the magnitude goes down faster, then the frequency increases, then the derivative actually converges. On the other hand, if the frequency increases faster while the magnitude decreases slower, then the derivative would actually blow up to infinity, right? The third case is, which is exactly what's happening here, is that the magnitude decreases like 1 over t, while the frequency increases linearly to t. So neither wins out, and the derivative, which in this case is the derivative of the error, right? Because the true derivative is equal to 0, actually never increases nor decreases. So we get actually a behavior like what we saw before, right? You can actually take the derivative of this function analytically with respect to s. You're going to see a t jumps out that cancels with this t, right? And that the error basically never goes to 0.
So, I mean, inside the parentheses, the value is between, like, let's say, it's going to be 0 and 2. Right?
Yeah, it's going to be between 0 and 2, yes.
So it never goes beyond that value. So how, as you said, the j bar goes to
J bar goes to 0, right? Because what's in the parentheses is never goes above 2, but there is a 1 over t, right? So basically the whole j bar t actually converges to 0, which is the true j bar.
What about the frequency you mentioned? If the frequency changes?
Yeah, but the frequency of this function, I mean, let's actually plot it, what it looks like, right? So let's plot it. T is equal to, let's say, 4t in 10, 20, 50, and 100. And plot s and 1 over t times, well, 1 over 2 pi times 1 plus s times t, right? That's this thing, times 1 minus cosine 2 pi 1 plus s times t, right? So that's what the function looks like. I think I need one more parenthesis. Okay, so blue is t equal to 10, right? As we can see, and the orange is t equal to 20. Let me just legend, same thing. Okay, as we can see that as t increases from 10 to 20, 50, 100, the absolute magnitude of this function, which is our t bar averaged over finite time, actually decreases linearly with respect to this big T, right? But so does the frequency of oscillation increase. So if you look at how much error I have in the derivative of this function, right? I know the true derivative of, the infinite time j bar is equal to 0. So the derivative of the true j bar with respect to s is also 0, right? And the error in the derivative of the finite time approximation would actually never decrease to 0. Yeah. Yeah, go back to my notes.
So we now take the derivative of that expression, we get this error that we don't get the right derivative.
Yeah, right.
Taking the derivative of j bar. It's supposed to be different from taking the derivative inside the integral, right?
Sorry, what's the question?
Yeah, my question is, in the very beginning, we were discussing that it's not going to be the same taking the derivative of j bar, right?
Mm-hmm.
Than taking the derivative inside the integral.
Yes.
So if we take the derivative inside the integral, do we get 0 or not?
Take the derivative into the integral actually doesn't make a difference, right? So for example, let's actually do it over here. Let's see what does it mean by taking the derivative inside the integral. So if we solve the linearized equation or tangent equation, what is that, right? It's d let's say, let me still denote V as the perturbation in the solution. dV dt is equal to what? It's going to be equal to, the right hand side is the derivative of the right hand side with respect to s, right? Which is equal to 1, right? And by the way, this V is not going to be restricted from 0 to 1. It actually would increase linearly. So V would be actually is going to be equal to T. Okay, so then if you take the solution, and what is dj dx? dj dx is going to be, oh, let me just say dj ds is going to be dj dx, which is cosine 2 pi x, right, times dx ds, which is equal to v and equal to t, right? So dj ds would be equal to that. Okay, and taking the derivative inside the integral means you are having dj bar t ds would be equal to the time average of integral from 0 to t cosine of 2 pi x times t dt, right? Again, you are averaging over length time t, something that grows linearly as a function of big T, small t, right? Okay, so we are going to see that of course if you substitute x into this equation and integrate analytically, you're going to actually get something. You're going to get the same thing as the derivative of this function, which is never going to go to 0.
So that time 1 over t cancels out with t in the
yes, right. This t cancels. I mean, the magnitude of this integral, right, would also grow linearly with respect to big T, right, and that cancels with the 1 over t.
So it never goes.
Never goes to 0. Yes. Okay, so this is really an illustration of the problem that we are going to encounter again in chaotic systems, except for in a chaotic system, the frequency of the oscillations is, so in a chaotic system, right, instead of having a V that grows linear in time, we are going to have a V that grows exponential in time. Okay, and as a result of that, you're averaging over something that grows exponentially. So, and in another sense, that the frequency of this oscillation would be an exponential function of big T, while the denominator is still big T, right? So the problem is of the same nature, but much more severe in the sense that you are no longer going to get an error in the derivative that's bounded. You are actually going to get an error in the derivative that also increases exponentially.
So which term is gonna be correct? So 1 dj bar ds is 0, right? The other one is not 0.
Yes, and the 0 derivative is analogous to the derivative we want to compute, right? Because it is actually because in a real system, like no matter scientific or engineering system, right, we have no control of the initial condition precisely, right? If we are looking at the long time behavior of a system, we have to assume that we don't have precise information about the initial condition, because the solution after a long time is going to be so sensitive to the initial condition that it doesn't make sense to assume we know the initial condition so precisely. Then the only prediction you can make to the system is the statistical quantities, right? So for example, if you are looking at a nuclear reactor or an airplane, right, and the smallest turbulent scales is usually in milliseconds or even microseconds, right? And the only thing you hope to predict is the long time averaged, for example, heat transfer rate or drag on the airplane. So, and this is something you want to, for example, optimize and design, and therefore you want to take the derivative of the quantity of interest averaged over a long time to certain control parameter or design parameter of the system. And that's the dj bar ds we are interested in, right? And it is not the dj bar with a big time t, because the dj bar with the big time t actually doesn't just depend on the system, it also depends on the initial condition, the particular initial condition.
So should we write, for example, for the one that is 0, it's d over ds j bar, right? It's dj bar ds.
Yes.
So 0. But for the second one, we write dj over ds, then average it and say everything is in bar.
Oh yes, that's correct. So for the second finite time average, you can also write it as a djds averaged over finite time, right? For the first, you cannot do that because the bar denotes an infinite time average, and you cannot. We have shown that this is a case where we have shown that an infinite time average cannot commute with the derivative. But a finite time average has no problem commuting with the derivative, right? You just need to take a derivative into the integral, which is completely valid if both the bounds of the integral does not depend on the parameter. All right. Okay, any other questions on what we are seeing here? All right. So now let's discuss what are the ways to actually compute the derivatives in a good way. Okay, and it turns out that we have a lot more tools to do this for periodic systems than for chaotic systems. So we will in the first we'll discuss the easiest way to deal with the problem, but that only works for periodic systems so far, right? So maybe you can as a part of if you can think about how do we generalize this method into chaotic system, that would be really useful. So far, nobody was able to generalize the windowing method to work on chaotic system first yet. So what is the windowing method? The windowing method aims to increase the rate of convergence of J bar. Okay, remember, like the computation we have here is, does the J bar with a finite time t converge to J bar at a faster rate, or does the frequency increase at a faster rate? If the frequency increases not as fast as the rate over which the whole thing decreases, then we have hope that the derivative is actually going to converge, right? So that is basically looking at this plot. So if instead of the magnitude goes down linearly, if the magnitude goes down, for example, quadratically, right, then not only would the magnitude go to 0, but also the derivative would also go to 0. That is the goal of the windowing method. We also discuss a second method, that's what we call a time dilation method. That's working exactly on the second part. That's trying to make the frequency of the oscillation not increase linearly, right? Rather working on the magnitude of the oscillation. So we'll first look at the magnitude of the oscillation. So the windowing method is a method of computing a finite time average that's more accurate than just taking the time average, right? So it basically focuses on the fact that if you take a finite time average, and that average is not over an integer number of periods, then the endpoints of this aperiodic averaging actually introduces very significant amount of error. The windowing method aims towards basically averaging over an oscillatory function, but it's a weighted average, where the weight is bigger than 1 in the middle and it decays to 0 at the two ends. So let's, for example, apply the windowing method exactly on this made-up problem to see how that helps. Okay, so the made-up problem, we have an objective function that's a sinusoidal function, right? Okay, and so the windowing method, so that's computing J bar, still with a time big T, but windowed. It's going to be equal to 1 over T, integration from 0 to T, J at time T, but times a windowing function, okay? That is a function of T divided by T. So the argument of the windowing function basically goes from 0 to 1. 0 is the beginning of the window, 1 is the end of the window. Okay, the windowing function is usually a function. So the windowing function W of x has to satisfy needs to satisfy the integral from 0 to 1 Wx has to equal to 1 exactly. All right, so that basically it makes sure that after applying the weight, the average weight is equal to 1, right? So that we're still going to get a correct average. If, for example, the signal j is a constant function, right, then that means this constraint to make sure that the window, the average, actually averages a constant function correctly. All right. Okay, so a typical windowing function looks like this. A typical windowing function looks like, well, the actually most trivial windowing function is a constant function, right? From 0 to 1, and the value is equal to 1. It's equivalent to not windowing at all. It's just the plain average. And we can have a function that just looks like this. It goes to 0 at the two ends. Right? A typical such function is Wx would equal to just a sinusoidal function of sine of pi x. Okay, and of course, if you integrate sine of pi x, it's not going to be equal to 1. So we have to multiply it with something. What do we need to multiply for the sine of pi x to average to 1? It's pi, right? Okay, so multiply by pi. If you integrate this from 0 to 1, it's I think, let's see, pi x, we would get cosine goes from 0 to second. We would get cosine from 0 to pi, which is equal to 2, right? So we have to multiply by half pi to get it to integrate to 1. All right, so this is one windowing function, and let's actually apply that windowing function to our artificially made up problem to see how that actually helps. So remember, our artificially made up problem has j equal to, what was it? Sine of 2 pi 1 plus s times t, right? Okay, and so let's go back to here, and let's copy the same thing here, and let's first make sure that we are able to reproduce the same oscillatory behavior when we are using a square window, like basically not windowing. And t would be, let's say, length space of 0t, and let's use t times I don't know, 100 plus 1 as my averaging. So basically my j bar would be equal to sine of 2 pi times 1 plus s times t, right, averaged. So actually I need to make a new dimension because s is a so basically I'm making the second dimension to be the time dimension and the first dimension to the dimension of s. All right, so actually j is equal to that, and j bar would be equal to j dot averaged over the second dimension. So I'm going to plot j versus j, s versus j bar. All right, so okay, so it's the same behavior as previously. So basically I'm reproducing this using a square window, not windowing at all. Now let me just make another plot. No. Okay, so I'm plotting this first one. I'm going to make a second. I'm going to make a j bar 2 is equal to j times pi over 2. So that's times sine of t divided. Okay, so pi times t divided by big T. Dot mean 1. All right. Actually, s and j bar 2. Our fixed size is not spelled correctly. Okay. So yeah, so actually let's make it side by side so it's easy to compare. So on the left hand side, we have the non-window, the plane average. On the right hand side, we are using our simplest windowing function, like the cosine window. What is obvious is that on the left hand side, right? So as you increase the length of the time averaging by a factor of 2 from the blue to orange, we are reducing the magnitude exactly by a factor of 2 almost. On the right hand side, you can see the magnitude of the oscillation is reduced by actually a bit more than a factor of 3, right? And at the end, you see the red line. I mean, the blue line looks as oscillator as this one, but if you look at the y-axis, it's actually less. And if you look at the red line, it's obviously much less oscillatory, right? Much less magnitude than on the left-hand side. So the windowing actually improves the order of convergence as t goes to infinity of the objective function without increasing the frequency of the oscillations. Okay, as a result of that, if you use the windowing function on the objective function, right, you can show that if you take derivative, you can now actually commute the derivative with the infinite time average, just because the frequency now increases at a slower rate compared to the decrease of the magnitude of the oscillations. Okay, and you can actually invent even better windowing functions. So this windowing function makes sure that the magnitude of the oscillations decreases like 1 over t squared. Okay, and you can also construct different objective functions that makes the objective function decrease at the even faster rate, like 1 over t cubed, 1 over t fourth, etc. But up to now, nobody has able to find an windowing function that makes the objective function makes the oscillation decrease at a sufficiently fast rate to overcome like the oscillation of a chaotic dynamical system yet. So that's why this method has been working. It's a very easy method to implement, works well for periodic oscillations, but we haven't been able to make it work for chaotic systems yet. So starting from the next lecture, I'll explain a different method that aims to reduce the oscillations, right, rather than decreasing the magnitude of the oscillations. It's to remove the frequency, remove the increase of the frequency of the oscillations. Okay, so that's time dilation. That's the method that we have successfully used in chaotic systems, but that actually requires a lot more involved algorithm to deal with the shift in the distribution on the attractor. Okay, so we'll see you next week to discuss that. And after that, we'll go to chaotic systems. All right.
GitHub, you had a code for finding the sensitivity analysis, and then you used windowing.
Right.
There, but it was for chaotic systems.
Yeah. So for chaotic systems, windowing helps, right? Because it removes the magnitude of the oscillations, but using only windowing by itself, it doesn't work. I still have windowing because windowing always helps in that it reduces the magnitude of this, right? So only windowing though is not enough for chaotic systems.
And it also works when we want to average lift or drag coefficient for a not very long time.
Yes.
Let's say because the idea is that after 4 limit cycle, or we can capture the lift and drag coefficients and time average on that.
Yeah.
But before that, they say no, it's a bit tricky because in the it's in transition mode.
Yeah.
So if we use this windowing, will we get better results?
You almost always get better results when you're averaging either a periodic signal but over a non-integer periods, or averaging over a non-periodic signal, right? So windowing almost always helps in these cases.
It's always plus.
Yeah, I yet have to find a case where the square windowing is actually the best. Unless you're averaging over a periodic signal over integer periods, right? I mean, that's the only case where like a square window outperforms all other windowing. Otherwise, there is some type of window that actually would help compared to the square window.